All right, so chapter 6 is all about logarithms. I'm trying a new video recording, so we'll see how this goes. Something I have to try for the district. All right, so logarithms are extremely important because they help us with exponential functions. So we're going to look at a couple things first. I want you to think about what are some different inverse operations. You know, this is one of my big pet peeves, the whole inverse, opposite, reciprocal, all these things. Remember, an inverse can undo something. So, like when we think of add, the inverse is subtract. Think of multiply, and this is back and forth, right? The inverse of add is subtract. The inverse of subtract is add. They go back and forth. We also have multiply and divide. And what we're going to get into now is exponential and logarithmic. So this is why we need logarithms. Logarithms are the inverse. Sorry, my handwriting's so sloppy. Logarithms are the inverse of exponential. It's not quite best English, but you know what I'm getting at. Okay, so one of the things we're going to talk about is rewriting. Think way back to grade school. Sometimes you may have had to rewrite an addition problem using subtraction. So we could say 5 minus 2 equals 3, where these are both using same sets of numbers. This is the addition statement. This is the subtraction statement. Well, you're used to exponential functions. 2 to the third equals 8. So when I rewrite this using logarithms, the base of this is 2. 3 is the exponent. The base is 2. The base of the log goes into this little corner here, little subscript, and we kind of go all the way around. Log base 2 of 8 equals the exponent every single time. So the base here goes to the base here. The exponent goes at the end. All right. First of all, it's important to remember the common log is the log in your calculator, and that's log base 10. You don't actually see, this is an implied number. Kind of like when you write x, you know the coefficient is 1 if there's not a number there, and the exponent is 1 if there's not a number there. If you don't see a number in the base of the log, it's always base 10. And that we call that the common log. So when I'm rewriting exponential forms and log base 10, notice both of these are base 10. I don't have to include that little 10. We say that log of 100 equals 2. Log base 10, don't have to write it, of 1,000 equals 3. All right, so logarithm base 10 just says the logarithm in base 10 of a positive number is the power of 10 that it must be raised to get that number. So log base 10 of 10 to any power will always equal the number. So let's think about how that works up here. Log of 100 equals 2 because 100 is 10 squared. So I want you to think of it this way. This is base 10. When we solve an equation like x plus 3 equals 5, we can subtract 3 from both sides. We use the inverse to cancel this out to get x by itself. Because the base of the log matches the base exponentially, the logs and exponents are inverses. So log base 10 cancels out the base of 10. That's why this whole thing equals 2. Oh, so I guess we just did this, didn't we? because I know this is base 10 if there's not a number there. I need to replace 100 with a power of 10. 10 is 10 squared, so the base of the log cancels out the base exponentially, and my answer is 2. The key is to always rewrite this number as a power of 10. So I know this is log base 10. How do I rewrite the fourth root of 10? That's 10 to the 1/4. Since the base of the log is 10 and this is 10 to the 1/4, the base 10s cancel and 1/4 is my answer. So vice versa, we can also start with the answer and put it back into 10 to a power. So using this right here is just an example. 8 is like my x. This equals 10 raised to the log of 8, because these would cancel. Exponential and log match, the bases match. That's how this works. What the book wants you to replace this with is 10 to a power. Actually plug log 8 and enter that into your calculator. And what do you get as an answer? Remember, always using 3 sig figs, 0.0 or 0.903. So you rewrite this statement using this as an example, and then just plug log 8 into your calculator and replace it. So 800 equals 10 raised to the log of 800. Bring 800 down. 10, what is log of 800? 2.90. And literally, if you plug this into your calculator, 10 raised to the 2.90, you're going to get around 800. All right, so 0.08 equals 10 raised to the log of 0.08. Find log of 0.08 in your calculator. That's negative 1.10. If you use 3, you need 3 significant figures. All right, so if we look at the log of 2, I get 0.301. If I look at log of 20, I get 1.301. So it should make sense. Log of 20 equals log of 2 plus 1, because log of 20 is 1.301. Log of 2 is 0.301 plus 1. Oops. And 1.031 equals 1.301. All right. And that's it.